Good morning, students. Today we are going to study the next chapter of strength of materials, that is columns and torsion. First of all, we will take a look at columns. Columns and buckling. When we speak of columns and buckling, we are talking about members loaded in compression, often axially loaded, although columns may be loaded eccentrically. It means कि we are talking about columns which are loaded in compression like this, often axially. We always exert pressure on the axis of the column, although sometimes it may be eccentrically also. We also tend to think of columns as vertical members. However, the formulas we will utilize also apply to horizontal compression members or to compression members in general. It means जो formula हम use करेंगे हमें लगता है कि वो सिर्फ vertical के लिए है, but अगर column को हम horizontally position कर दें उस पर भी वही formula applicable होगा. For instance, compression members of a truss may be considered to be columns pinned at each end point. Like एक ट्रस के अंदर जो कॉलम्स होते हैं, we can consider them as columns pinned at each end point. ये कॉलम्स की एंड पोजीशंस होती है कि हम उसको पिन कर सकते हैं या फिक्स कर सकते हैं. We will discuss these positions, end positions of the columns in detail. After this, now first of all, types of columns. Columns may be divided into three general types. तीन तरह के columns हम divide कर सकते हैं. First can be a short column, second intermediate column, and the third one is long columns. The distinction between types of columns is not well defined. इनके बीच में डिफरेंस कोई बहुत ज़्यादा वेल डिफाइंड नहीं है. वी कैन नॉट से कि पर्टिकुलर इतने लेंथ से ज़्यादा होगा उसको हम लॉन्ग बोलेंगे या इससे शॉर्ट होगा उसको शॉर्ट बोलेंगे. बट yes, we have certain specifications. A generally accepted measure is based on the slenders ratio. According to slenders ratio, एक slenders ratio एक हम expression निकालेंगे. उस expression के according जितनी उसकी length आएगी, अगर वो slenders ratio के according intermediate में fall कर रही है तो we will say the column is intermediate. If it is a short column, then we will say it is a short column. And if the slenders ratio is higher than a certain limit, we will say the column is a long column. Now, what is slenders ratio? Slenders ratio is the effective length of the column divided by its radius of gyration. Slenders ratio क्या होती है? इफेक्टिव लेंथ, जो कॉलम की इफेक्टिव लेंथ है, डिवाइडेड बाय रेडियस ऑफ जायरेशन. हम इफेक्टिव लेंथ भी निकालेंगे. लेंथ और इफेक्टिव लेंथ में एक डिफरेंस है. वो डिफरेंस भी कैसे निकलेगा? अकॉर्डिंग टू द एंड पोजीशन ऑफ द कॉलम्स, कि वो फिक्स्ड है या पिन्ड है. उसके अकॉर्डिंग वी विल फाइंड आउट द इफेक्टिव लेंथ. एंड व्हाट इज रेडियस ऑफ जायरेशन, वी विल आल्सो डिस्कस इट. And when we will divide the length of column, effective length of column divided by radius of gyration, it will give slenders ratio. The radius of gyration is the distance from an axis which, if the entire cross-sectional area of the object or beam or column were located at that distance, it would result in the same moment of inertia that the object possesses, or it may be expressed as radius of gyration rxx is equals to moment of inertia around on xx axis divided by the area of cross section whole raised to the power 1.1 by 2. So slenders ratio is equals to effective length LE divided by the radius of a gyration R. Notice that we have put a subscript E by the length of the column. This is to indicate that depending on how column is supported, जैसा मैंने आपको बताया था कि कॉलम को किस तरह से सपोर्ट किया है उसके अकॉर्डिंग उसकी इफेक्टिव लेंथ निकालेंगे हम. We do not use the actual length but an effective length. The effective length is given by LE is equals to KL, where LE is the effective length, K is called effective length constant, and L is the actual length, and the K depends on how the column is supported. For when a column is pinned at both sides, we call it pinned, K is equals to 1. When the column is fixed at one side and pinned from the other side, the K will be 0.7. When the column is fixed at both the ends, we'll say that the K is equals to 0.5. When one end is fixed and the other is free, then effective length constant will be K will be equals to 2. So for suppose a length of the column is around 1 meter, but it is fixed from one end and free from the other end, we will say the effective length is equals to 2 multiplied by 1, that will be 2 meters then. Now this is the diagram. ये वही चीज़ शो कर रहा है जो हमने पिछले आर्टिकल में पढ़ी है. It is showing how the column is end positions vary. पहले डायग्राम ए में दिखाया हुआ है कि it is pinned and pinned column, दोनों जगह से दोनों end positions पे ये pinned है. Then effective length LE will be equals to L because K is equals to 1. दूसरे डायग्राम में एक end fixed है और दूसरा pinned है, and LE is equals to 0.7 L, then K is equals to 0.7. and तीसरे डायग्राम में एक एंड दोनों एंड्स फिक्स्ड हैं. अगर दोनों एंड्स फिक्स्ड हों तो K effective length constant is equals to 0.5. So effective length is equals to 0.5 multiplied by the actual length. And the last is when one end is fixed and the other end is free, then K will be equals to 2 and effective length is equals to 2L. A generally accepted relationship between the slenders ratio and the type of column is as follows. जैसे मैंने आपको शुरू में बताया था कि हम स्लेंडर्स रेशो की एक लिमिट के अकॉर्डिंग बता सकते हैं कि कॉलम शॉर्ट है, इंटरमीडिएट है या लॉन्ग है. सो अगर स्लेंडर्स रेशो 0 से 60 के बीच में आती है, then we will say that the column is a short column. अगर स्लेंडर्स रेशो LE by R 60 और 120 के बीच आती है, then we will say that the column is of intermediate length. If it is between, the slenders ratio is between 120 and 300, then the column will be said to be a long column. Now take a look at short columns. When the slenders ratio is less than 60, a column will not fail due to buckling. As the ratio of the column length to the effective cross-sectional area is too small, means एक short column एक ऐसा column होगा, it will be like this much of length and this much of width. अब इसको अगर हम top से pressure exert करेंगे, it will not fail due to buckling, we can say. Rather, a short or thick column axially loaded will fail in simple compressive failure. वो buckling नहीं होगा, मतलब उस column के अंदर इस type की कोई buckling नहीं आएगी, but it will fail due to simple compressive failure. That is when the load by area of the column exceeds allowable stress. वो तभी होगा जब जो फोर्स है लोड बाय एरिया और एक अलाउएबल स्ट्रेस से ज़्यादा हो जाएगी, तब उसमें कंप्रेसिव फेलियर आ जाएगा, बट कॉलम के अंदर बकलिंग नहीं होगी. बकलिंग लाइक व्हेन वी आर एक्सर्टिंग प्रेशर लाइक दिस और ये इस तरह से बकल हो जाता है, वो बकल नहीं होगा. Long columns and Euler's equation. In 1757, Leonhard Euler developed a relationship for the critical column load which would produce buckling. तो 1957 में ऑयलर्स द्वारा एक फॉर्मूला बनाया गया था जिसमें हम क्रिटिकल लोड बता सकते हैं किसी कॉलम के लिए जिस लोड पे वो कॉलम में बकलिंग स्टार्ट हो जाएगी. A very brief derivation of the Euler's equation goes as follows. A loaded pinned column is shown in the diagram. You can see this side it is also pinned and this side it is also pinned. A top section of the diagram is shown with the bending moment indicated. This is a diagram for the top corner, you can say. A bending moment M is there. We are exerting a load P from both sides and at a distance x from the top, and the deflection distance is y. Then we can write that M, the bending moment, is equals to minus P multiplied by y. We can also write that for beams columns the bending moment is proportional to the curvature of the beam, which for small deflection can be expressed as m divided by EI is equals to, where m is the bending moment, E is the Young's modulus and I is the moment of inertia, then it will be equals to d2y by dx square. Then substituting from equation 1 was this, m is equals to minus py. Substituting m is equals to minus py in this equation 2, we obtain d2y by dx square is equals to minus p by eiy, or d2y by dx square plus p by ei multiplied by y is equals to 0. This is a second order differential equation which has a general solution form of y is equals to a sine under the root p by ei multiplied by x plus b cosine under the root p by ei multiplied by x. We next apply boundary conditions. At boundary conditions, obviously y will be 0, x will be 0, and at the other point y will be 0 and x will be equals to L, the total length of the column. That is, the deflection of the column must be 0 at each end. Obviously, when it is pinned or at each end, then the deflection at each end will be 0. Applying these conditions gives us the following results. For y to be 0 at x 0, the value of b must be 0 since cosine 0 is equals to 1, while for y to be 0 at x is equals to L, then either a must be 0, which leaves us with no equation at all. If a and b are both 0, or sine under the root p by ei multiplied by L is equals to 0, which results in the fact that under the root p by ei multiplied by L is equals to pi, and we can now solve for p and find the critical load PCR is equals to pi square ei divided by L square, where PCR stands for critical load, which can be applied before buckling is initiated. So this is the form Euler's equations and for critical load. By replacing L with the effective length LE, which was defined above, we can generalize the formula to PCR is equals to pi square EI divided by the square of effective length LE square. This is also the other form of Euler's equation, which then applies to the pinned, fixed, fixed and fixed free columns. इस इक्वेशन को हम हर कॉलम के लिए अप्लाई कर सकते हैं. जो पहले इक्वेशन निकाली थी Euler's equation, that was only for the column when it is loaded, it is pinned at both ends, and now when we have replaced L by LE, the effective length, then the equation becomes applicable to all the end positions: pinned, fixed, fixed and fixed free. This is a form of Euler's equation. Another form may be obtained by solving for critical stress. अभी हमने critical load निकाला. This is the formula for critical stress. Stress is equals to load divided by area. So we can say that it is PCR divided by A, pi square EI divided by LE square multiplied by A, and then remembering that the radius of gyration Rxx is equals to I by A under the root, and substituting we can obtain the critical stress is equals to pi square E divided by LE by R whole square. So we have substituted Ixx by A as R, and since was in the under root for radius of gyration, we have used here the square, which gives critical stress in terms of Young's modulus and the column material and the slenders ratio. तो ये एक इक्वेशन हमारे पास आ गई है क्रिटिकल स्ट्रेस की in the terms of Young's modulus and the slenders ratio. Some additional points to be mentioned: the slenders ratio, effective length by the radius of gyration, depends on the radius of gyration. Rxx is equals to Ixx by A whole under the root, and Ryy is equals to moment of inertia along YY axis divided by the area of cross sections and under the root, which in turns depends